And now that we've done our curve sketching and we have a good understanding of extremas, we're going to solve some optimization problems. You've actually been doing these over the years. Now we'll use derivatives to make solving them even a little bit easier. These learning goals should look familiar. They're the same as the last time we were solving problems in the calculus part of the course. One of the common types of questions we'll see with this type of optimization problem is using geometry. So we're going to do one of those today. So a farmer has 1,000 meters of fencing to enclose a rectangular field. One side is against the road that already has a fence. How can the farmer create this field so that the area will be maximized? So it might help you to draw a picture for questions like this. So we've got a roadside that's already fenced, and we want to build a rectangle. We need to figure out what those dimensions are going to be. So let's call the width x. And since we know the total fencing they have is 1,000 meters, that will make the piece left over for the length. 1,000 subtract the 2x that's being used for the two sides of the widths. And of course, we're going to write ourselves a let statement. So we should be able to form a model here for the area. Because the area is length times width. And you may even remember as far back as grade 9, we started doing problems like this. Again, in grade 10 and 11, because you can see this is quadratic, so we can solve it using a parabola and finding the max point. In grade 9, we did it through exploration, but there is a pattern to it. So you may even be able to kind of remember what this turns out to be from that. But let's take a moment to think at least a little bit about what's going to be reasonable here. Well, we know that our domain can't go below 0 because it won't make sense if our width is 0. It would not be possible to actually form a rectangle with no width. And the same would be true if the length was 0. So if x got to be so big that you couldn't have an actual length, that would be a problem. So it makes sense that x is going to be between 0 and 500, which means we actually have a defined interval for this. So it's probably going to be pretty reasonable that the answer is somewhere in between here. And again, you might remember the pattern for this. Maybe it'll come back to you once you see the answer for one of these questions. So since we're looking for the maximum area, that means we're looking for a potential extrema point. I'm going to expand this function just because it's easier to take the derivative of. So the derivative will be 1,000 subtract 4x. And extrema points can occur when the slope of the tangent is 0. So we're looking for where this is going to be 0. And it turns out that x would be 250. Now, because this is a defined interval, we have to also check the endpoints to make sure. Now, I know that we can figure out from this that the parabola is going to have a concave down, so it makes sense that we already know that x equals 250 is the answer, but we may not always know this depending on the question. So let's just remember that when we have defined intervals, we're going to double check it with any endpoints as well. So we check for 0, because that's one of our endpoints, and that area will be 0. We check for what we think is an extrema, and plug that in. And we get this clearly larger than 0. And of course, we're going to test to the other extrema as well. And that one also turns out to be 0. So therefore, the farmer should build his rectangular field to be 250 meters by 500 meters to maximize his area. Another common category will be economics. So we could be talking about things like revenue, profit, cost, and sometimes you may even see science examples. This kind of combines two of them. So we have a cylindrical chemical storage tank with a capacity of 1,000 meters cubed. So that's the volume it needs to have. It's going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. The specifications call for the base to be made of a sheet steel that costs $100 per meter squared. The top to be made of sheet steel that costs $50 per meter squared, and the wall to be made of sheet steel that costs $80 per meter squared. Is it possible to build this at all in the room? And then how can we minimize the cost of the steel needed to construct it if it is possible? So we're going to start with that first part to find out what's possible. And it's also going to help us to actually come up with a domain restriction for our model as well. So for some of you, it might help to kind of form a quick drawing. So we're looking to build something that's a cylinder, and it has to happen in a room with specific dimensions. So the question is this possible? We know that the room is 11 meters tall. We know that it's 15 by 12 meters on its base. And we need to figure out what's the radius of this cylinder going to be and what's the height of the cylinder going to be. Whoops. I wrote height, even though I'm talking about the radius. Always remember to give your let statements units. They should be specific, so it's the radius, that's the specific piece, and the unit is meters. And what we need to do is figure out what's possible. So looking at the dimensions of the room, we can see that the diameter of that cylinder can't be bigger than 12 meters. So that actually tells me the radius has to be less than 6 meters. So that's helpful. And we also know that the height has to be less than 11 meters based on the room. And if we allow the height to actually be 11 meters, then we know that the area will have to look like this because the capacity needs to be a minimum of 1,000. So that will give you that your radius has to be greater than or equal to 5.38 meters. So it does seem like this is possible. And we've also created a potential restriction for our model here, where the radius has to be between 5.38 and 6. So now we can start to figure out how to minimize this cost. We know that the cost related to the base comes in at $100 per meter squared. So that's $100 times the area. And The cost for the top then is 50 times the area of the top, and for the wall is 80 times the area of the wall. And since we want to build something that has the capacity of 1,000, we know that's true, which means we can rewrite H using it in terms of R. So we're going to make use of that as well. So our cost function in terms of the radius will be the sum of those three pieces. So 150 pi r squared plus 160 pi r times our height. Which simplifies to that. And we know that this has a domain restriction. So again, we have a defined interval. So since we're looking to minimize, we know that we're looking for when the derivative is 0. So we need to find the derivative. And we need to know where that is going to be 0. So to solve this, I want to multiply both sides by r squared. So we still get 0 on the left, 300 pi r cubed now, minus 160,000, and we're going to rearrange this equation. And we get that r is approximately 5.54 meters, which does lie within our domain. So it is a value that we're going to need to test. So we're going to find out the cost at 5.54, which will turn out to be approximately 43,344. The cost at 5.38, because again, we have to test the ends of our intervals because it's a defined interval. And that's 43,380. So you can kind of see why we're testing this, especially since we don't totally know what this function looks like. And the cost at the other endpoint, 43,631. So it does turn out that we get our minimum value. Get our minimum value here. So therefore, the storage tank can be built at a minimum cost with a radius of 5.54 meters. And we really need to figure out this height as well. Which turns out to be 10.37 meters. There we go.